Hello and welcome. In this video, we're going to be looking at common functions that are going to be used all the time in calculus. In part one, we looked at algebraic functions, and in part two, we're going to be looking at trigonometric functions. It's a fairly brief overlook of trigonometric functions. We'll cover just the basics that you need to know to get started. You may notice that this is a little different layout than our last video. This is the home office. I'm trying a little different setup, so I'm hoping it'll work out okay. Well, let's take a look at the notes here, and I'll start drawing a unit circle is going to be our first approach. Okay, here's the unit circle. And when we say unit circle, that means that the radius of this circle is equal to 1, and it is centered at the origin. So I'm going to just draw the x and y axes here. And because it's a unit circle, one point that is on this circle is going to be the coordinates 1, 0. Now, from that point, if you can imagine just traveling around the circle, you've got a choice of two different directions. Now, we choose to treat the direction counterclockwise as a positive direction, and we choose to treat the clockwise direction as being negative. And it may be fairly common to think of a full circle as being 360 degrees, but in calculus, we use radians. Now, in radians, if you travel all the way around the circle, you will have traveled 2 pi radians. The advantage to using radians is that it links angles to distance. If this is a circle of radius 1, then we can talk about the angle we travel through being 2 pi radians, but also the distance around the circumference of this circle is also 2 pi. So that's why we're going to be using radians for this course. Now we'll define 3 basic trigonometric functions in terms of the angle. Now let's say that the angle is theta, but of course you could use any angle to use the angle. And remember that when we're talking about a unit circle, angle and distance around the circumference mean the same thing. Okay, so the basics here is sine, cosine, and tangent. Sine theta, if we start at that point 1, 0, and we travel around the circle and we end up at some coordinate further around the circle, we can go ahead and we can think about the angle that we've traveled through, which is theta, which is also the distance around the blue circle that we've traveled because it's a radius of 1. Sine theta is defined as the y coordinate. Now, in general, if this is not a unit circle and it's any circle centered at the origin with any radius r, we can actually also use y over r, the radius of the circle. Because r is equal to 1, in this case on the unit circle, it's just the y coordinate. But it is important to remember that y over r for when we get to our second approach later. Cosine theta is going to be just the x coordinate of a point around the circle. If it's not a unit circle and it has a radius of r, then we can extend that to x over r. And tangent theta is the ratio of y over x. So you can just imagine that at any point around the circle, we end up at a point with an x coordinate and a y coordinate, and just using that information, we can come up with sine theta, cos theta, and tangent theta. Now remember, a full circle is 2 pi radians, so an easy conversion here is that 2 pi is the same thing as 360 degrees. Now you can also think about pi being just 180 degrees, and if you like right angles, pi over 2 is 90 degrees. And those are some pretty common angles that we're going to be using, so it might be good to just make a little table of those points. So let's start at the point 1, 0. And then let's go ahead and travel around the circle 90 degrees. Where do we end up? We'll end up at the top here with the coordinate 0, 1 because it's a radius of 1. travel around, well, sorry, that's pi over 2 radians. I'll mark that off. Now we're going to travel around to pi radians, and now we're actually in a negative x coordinate. So we'll end up at a point here, which is -1, 0. And if we travel around to the bottom of the circle, that's 3/4 of the circle, which is 3/2 pi. And that would be our negative y coordinate, 0, -1. If you go ahead and travel 2 pi radians around the circle, we'll end up back where we started. Because remember, this is our starting location. We can mark it off with a star there if we want. If you travel more than once around the circle, you'll end up back at the same places. If you end up traveling in the negative direction, you'll end up at those same points in reverse order. So let's make this table for theta, looking at 0, our origin, our pi over 2, pi, 3 pi over 2, and we might as well put 2 pi on there just to show that we end up back where we started. And we can look at the x and y coordinates on the unit circle. And so the first place we end up at is 1, 0, pi over 2, 0, 1, and pi halfway around the circle, -1, 0, 3 pi over 2 will end up at 0, -1, and 2 pi around the circle, we're back to where we started. All right, just using that information, we can fill in our main 3 trigonometric functions: sine theta, cosine theta, and tangent theta. All right, remember sine theta is just the y coordinate because this is a unit circle, so it starts at 0. And then we'll be looking at our next point at pi over 2 having a y coordinate of 1, at pi a y coordinate of 0, at 3 pi over 2 a y coordinate of -1, and at 2 pi we'll be back to being a y coordinate of 0. See if you can fill in the other ones. Okay, now you'll notice that after you've filled in most of these, you have a few different problems. Specifically at pi over 2 and 3 pi over 2, if you try to compute tangent theta, you're going to be dividing by 0. So there are a couple values around the unit circle where tangent theta is undefined. That's okay. We'll be looking at all the other points in between around the circle. So there are lots of other places where tangent theta is defined, but not just 0. Now there are 3 other trigonometric functions that we will be using, and these trigonometric functions are reciprocals. So we'll also be looking at cosecant theta, secant theta, and tangent theta. They're reciprocals, so cosecant theta is 1 over sine theta, secant theta is 1 over cosine theta, and tangent theta is 1. We'll also be looking at 3 other trigonometric functions, and these are reciprocals. Cosecant theta is defined as the reciprocal of sine theta, secant theta is the reciprocal of cosine theta, and cotangent theta is the reciprocal of tangent theta. So you can take the definitions of sine, cosine, and tangent, and then you can flip those fractions upside down to get the definitions of cosecant, secant, and cotangent. Now one other fact, if you notice, tangent theta is y over x, which, if we're looking at a unit circle, or even if we're looking at any circle of radius r, is exactly the same thing as taking sine theta divided by cosine theta. And that's a major identity to know. Now, because cotangent theta is the reciprocal of tangent theta, cotangent theta, if we take that fraction and take its reciprocal, is the same thing as cosine theta over sine theta. Okay, now the unit circle approach is just one of 2 approaches we want to look at, and it's particularly useful for looking at these 4 specific points. But you can take any value as an angle. It can be anywhere between 0 and 2 pi, or you can take an angle that is outside of a single circle, and you maybe want to travel around the circle many times and find out where you land up. And some of those coordinates are easier to find than others. And that's where I would recommend this second approach. Okay, in this second approach, we're going to be looking at triangles. And I've drawn the unit circle here at the center with radius 1, and you can see that origin point 1, 0. And remember our positive direction and our negative direction. So those haven't changed. Now I've picked a point on the unit circle here that isn't at one of the 4 major points we just looked at. So it's not the rightmost, leftmost, topmost, or bottommost point. It's some arbitrary point at some arbitrary angle, and we can call that angle theta. Now remember the definitions of sine and cosine and tangent, along with their reciprocals. I have given those definitions here using r as being any circle of radius r that we like. So if we wanted to find out the values of sine, cosine, tangent in any of these trig functions, we could also just as easily look at a point with that same angle, but on a circle of radius r. And what we can do as a nice little trick here is we can use a ruler, and if we take that point, and we'll call that the terminal point, because that's where you end as you go around the circle, and we'll connect that with a right angle to the x-axis. So it makes a right angle with the x-axis, and it is quite possible that if you've traveled into one of the other 4 quadrants here, that might have to be connected to the negative x-axis. But at any point around the circle, you can form a triangle. So let's just look at how you would do that with the 4 different quadrants. Okay, we're going to call this quadrant 1, since it's the first quadrant that you'd reach if you start at the point 1, 0 and you travel in the positive direction. Now, if you've made it to pi over 2, that would be the end of the first quadrant. Between pi over 2 and pi, this will be our second quadrant. Between pi and 3 pi over 2, this will be our third quadrant. And between 3 pi over 2 and 2 pi, or back to where we started, that would be the fourth quadrant. So you can see in quadrant 1, at any terminal point around the circle, we connect it straight down to the positive x-axis. And what if we end up in quadrant 2? In quadrant 2, if we were to look at a point, then we can go ahead and we can look at the angle. From where we started, the angle would end up being greater than pi over 2, but not quite as far as pi. To make a right angled triangle with the x-axis, this time around, we're going to be using a vertical line that connects that point to the negative x-axis. Once again, we've got a right angled triangle. In quadrant 3, now our angle has actually exceeded pi radians, and we're going to be looking at something pointing out here at a terminal point. And once again, if we want to make that into a right angled triangle, we're going to connect it with the negative x-axis. And in quadrant 4, somewhere between 3 pi over 2 and 2 pi, we're back to connecting that terminal point to the positive x-axis. And so you can see that as you travel around the circle, any terminal point can also be forming a triangle with the x-axis. The advantage to using triangles is that if we look at a couple very common shapes, we can actually go ahead and figure out what the horizontal and vertical lengths are, as well as the diagonal length. So if we take a look at a triangle in the first quadrant, we can take a look at these 3 different lengths. Okay, I've drawn a typical triangle here in quadrant 1, and this is what we call standard position. In standard position, you can see that the angle starts from the horizontal and works its way counterclockwise to the diagonal. We can mark these sides off as x, y, and r in order to make a sine, cosine, or tangent ratio. But there's another way to think about this, and you may be familiar with this already as another form of remembering what sine, cosine, and tangent are, is we can take a look at the longest side of a right angle triangle being the hypotenuse. We'll label this HYP for short. And the horizontal side here is closest to the angle, and so we call that the adjacent side. And the vertical part, Y, that vertical side is opposite the angle. So we'll label that OPP for opposite. So if we just focus on sine, cosine, and tangent, there are alternate ways to think about that in terms of triangles, and that would be looking at sine as opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. And you can remember that using SOHCAHTOA. Sine opposite hypotenuse, cosine adjacent hypotenuse, tangent opposite adjacent. Okay, well, let's take a look at some special triangles in standard position so that we can actually get the values of x, y, and r for a couple important triangles. The first triangle we're going to be looking at is if we take a square of unit 1. All right, so I've got a square, and each side is going to be a length of 1, and I'm going to cut that in half. All right, you can see I've cut that in half in such a way that I have formed a triangle in standard position in quadrant 1. And I've already got the opposite and adjacent sides. X and Y are both equal to 1. But what is the hypotenuse of this triangle? Well, we're going to be needing to use the Pythagorean identity. Now, you may be familiar with the Pythagorean identity as being a squared plus b squared equals c squared. But that's only good if I'm labeling the sides as a, b, and c. So you might want to remember this in terms of adjacent squared plus opposite squared equals hypotenuse squared. You can go ahead and you can compute the hypotenuse. 1 squared plus 1 squared is 2. If 2 is the hypotenuse squared, then the hypotenuse must be the square root of 2. It's not a great number, but it's certainly not too hard to remember. With these three sides, we can go ahead and we can look at what the angle is. The angle is 45 degrees, but remember that we're going to be using radians. So this is 1/2 of pi over 2, which makes this angle pi over 4. All right, so we can kind of add this to the table that we had previously. We already can look at sine of pi over 4 now as being opposite over a hypotenuse, 1 over root 2, which is the same thing as y over r, if you like. Cosine of pi over 4 is also 1 over root 2, and tangent of pi over 4 is awesome because it's opposite over adjacent, and 1 divided by 1 is 1. What about a second triangle? For our second triangle, we're going to take another common shape, which is an equilateral triangle. And so it's a triangle where all of the sides and angles are identical. Now we're going to cut this in half as well. And in order to avoid a few unnecessary fractions, we're going to let all sides of this equilateral triangle have a length of 2. So that means if I want to cut it in half, I can form a triangle in standard position. And I'm going to erase part of this triangle so that I just keep the part of a triangle that's in standard position in quadrant 1. A right angle triangle, and you can see the angle. Now, half of the length of the equilateral triangle would mean that the base here is equal to 1. Now, what is the third side? This time, you can use the Pythagorean identity to solve for the opposite side, and you should get the square root of 3. Now, what about the angle? In fact, we can use the same triangle and look at two different angles. Right now, the way I've drawn it, that angle is one of the 3 original equal angles of an equilateral triangle. And since triangles have all of their angles add up to 180 degrees, one of those angles has to be 60, so that there are 3 equal angles that add up to 180. So theta is 60 degrees, but what is that in terms of radians? You remember 180 degrees is pi, and this is 1/3 of that, so this angle is pi over 3. And so we can look at sine of pi over 3, which is opposite over hypotenuse. We can get cosine of pi over 3, which is adjacent over hypotenuse. And we can get tangent of pi over 3, which is opposite over adjacent. Now, if we use that same triangle, but we just rotate it slightly, we can use exactly the same triangle here in a slightly different orientation to look at the remaining angle, which I'll just indicate in red here. So what if we took that red angle and we put it in standard position? Okay, so you can see that I've taken that triangle and I've rotated it so that the red angle is now in standard position, and we can label that angle as theta. And I've got the 3 sides of the triangle already, but what is the red angle? Well, the 3 angles have to add up to 180 degrees, or pi radians. And we've got an angle of pi over 3, a right angle of pi over 2, and that means that the red angle must be pi over 6. And so we can fill in 3 more ratios. Sine of pi over 6 is opposite over hypotenuse, which is 1 over 2. Cosine of pi over 6, which is adjacent over hypotenuse, is root 3 over 2. And tangent of pi over 6 is opposite over adjacent, which is 1 over root 3. Okay, so to recap, we can make a table of all of the common angles that we've looked at. So it's looking at everything here in quadrant 1, as well as pi over 2, pi, and 3 pi over 2, which are just at the edges of the 4 quadrants. And we can fill in sine, cosine, and tangent. Okay, so we've got all of the basic values for sine, cosine, and tangent for a lot of the common angles now. So you should make sure you know this table, because we're going to be using these particular values much more frequently than other values. Pi over 6, pi over 4, pi over 3, and pi over 2 in particular are very useful angles. You can also apply this to quadrants 2, 3, and 4, just by remembering that when you form the triangle in those particular quadrants, that you may have to treat either the x or the y as being negative corresponding. Okay, now I know what you're thinking. You said this is going to be a brief video. Well, let's give you a little bit of a break here. You can say hello to my cat, who's been trying to help me record this whole time. And I promise this won't go on for too much longer. We just want to see if we can put this information together and form the graphs of sine, cosine, and tangent, the same way that we did with the algebraic functions in our last video. So let's put this together, and let's take a look at the graphs. Okay, using what we learned from the unit circle as well as the triangle approach, we can put a few points onto this graph, where if we use this horizontal axis and maybe treat this as though it was theta, we could go ahead and plot the values of sine theta. But we tend to use the horizontal axis as x. So you can just imagine that instead of talking about theta as an angle, we can use x as an angle. So let's go ahead and start with the unit circle points. At an angle of 0, we end up with sine of 0 being 0. At an angle of pi over 2, we end up with sine of pi over 2 being equal to 1. So we'll label 1 here on the vertical axis. At pi, that would be halfway around the circle, we end up back at 0. Sine of 3 pi over 2 is negative 1. We'll put negative 1 on the axis here. And at 2 pi, that's all the way around the circle, so we're right back to where we started at sine of 2 pi equals 0. Now we can also use the special triangle. In quadrant 1, we should also have pi over 4, pi over 6, and pi over 3. And remember that sine of pi over 6 is a half. Sine of pi over 4 is root 2 over 2, or 1 over root 2. And sine of pi over 3 is root 3 over 2. And so it's got this sort of smooth motion that goes up towards that top point. And as we travel through into the second quadrant, we come right back through all of those same y coordinates, and it's smooth heading right back down to 0. And if we're traveling halfway around the circle, all of the y coordinates so far have been positive. But if we go around the bottom half of the circle, we end up going through the negative values of sine, and we end up with a very similar shape except inverted as we come back around to 2 pi. Now, I haven't done the greatest job of drawing this. It's a little bit squiggly, but you can imagine this is a smooth wave as it goes all the way around the circle once. And if you continue going around the circle, then you'll end up going through exactly the same points. You're back into quadrant 1, and then quadrant 2, 3, 4. And if you're going backwards around the circle, you just end up in quadrant 4. And we have quadrant 4 here at the very last part of this red curve. You can just imagine it's exactly the same shape, traveling backwards as well. So we can try to do our best to sort of sketch it as we go around the circle in the reverse direction. Now, what about cosine? If we do the same strategy as we use with sine and start plotting the points around the 4 points on the unit circle, as well as the extra points that we used from triangles in the first quadrants, we can get a very similar shape, except that it starts at cosine of 0 equaling 1 and works its way down. It's essentially just taking the same wave shape as above and just shifting it slightly. Take it and shift it left by pi over 2. And again, it continues off if we want to go around the circle more than once, and it can also continue if you want to go around the circle in reverse order. Now, both sine and cosine repeat themselves every time we go around the circle. We say that sine and cosine are periodic. Every 2 pi, they repeat themselves. And so we call 2 pi a single period, and then it continues on in cycles after that. So a very basic property about sine and cosine is that sine of x is also the same as sine of x plus an additional 2 pi. Same thing with cosine. Now, what about tangent? Tangent is very different from the other functions. We do know that tangent of 0 is 0. And one of our favorite places on the tangent graph is in the first quadrant, tangent of pi over 4. Tangent of pi over 4, if you remember, is equal to 1. Now, unfortunately, if you remember, tangent of pi over 2 is undefined, but we can use a couple other points that we're familiar with using the special triangles when pi over 6 and pi over 3 are involved. Tangent of pi over 6 is 1 over root 3, so it's a very small value, and tangent of pi over 3 is root 3, which is a much larger value. At pi over 2, we have this very interesting behavior, because the ratio of y over x just keeps getting larger as we get closer to the top of the circle. We know that x is getting very close to 0, and y is getting very close to 1. And if you take 1 and divide it by a very, very small number, it gets very large. And we'll look at that behavior more when we talk about limits later on. But you can imagine that this is just going to be continuing to increase and increase, but it's undefined at pi over 2. We call that behavior an asymptote. But we'll talk about asymptotes a lot more later on. Now remember, in quadrant 2, we're still using the same ratio as tangent of the angle is the vertical or y coordinate divided by the x coordinate as you go around. And if you just get past that pi over 2, you still have a y coordinate that's close to 1 and an x coordinate that's close to 0. but the x-coordinate is negative, and 1 divided by a very small negative number is going to be a much lower negative value. And so you can kind of imagine that it's going to be somewhere down here, and it has more or less the same shape as it returns back to 0 when we get to pi. And if you continue around the circle, you end up with the repetitive behavior again. Remembering that at 3 pi over 2, tangent is undefined, so we have exactly the same behavior as what happened at pi over 2. And we can continue all the way around the circle, or if you want, you can go past that circle and continue the behavior, or we can go backwards around the circle. Now, you can see that this has a very repetitive behavior like before, except it repeats itself actually more often than sine or cosine. It repeats itself every half circle or every pi. So what we tend to think of as the typical shape for tangent is actually looking at the section from negative pi over 2 to positive pi over 2. So we're going to include this section here on the left as sort of the part of tangent that we remember the most between negative pi over 2 and positive pi over 2. And then it repeats itself every pi. So we say that tangent is pi periodic because it repeats itself every period of pi. And tangent of x is equal to tangent of x plus an additional half circle pi. And these are the basic shapes that you should know. So sine is a wave function that starts at 0 and goes up, comes down, dips below the x-axis, and comes back up if you're traveling around the circle counterclockwise. Cosine is the exact same shape. It starts at 1 when x is equal to 0, when the angle is 0. And tangent has these asymptotes at negative pi over 2 and positive pi over 2, and repeats itself every pi. Okay, well, I hope that sort of summarizes trigonometric functions, and that's about as brief as I can try to make it. I'm hoping that this is mostly going to be something that's familiar to you, but a lot of this, if you haven't done it in a while, is going to be a little bit of a struggle. So we'll be looking at it more in class, and there are lots of other online resources to look at. And take a little bit of comfort in knowing that we're not going to be using trigonometric functions heavily right away in calculus, but they are going to be coming up fairly soon, so it's good to start reviewing them now. Anyway, that's all for now. Thanks for watching.